So we left off talking about the standard hydrogen electrode and how using that, given the voltage of 0, it can help determine the standard electrode potential of different half-cell reactions. So let's look at a whole reaction where you have two half reactions, one of which neither of them are 0. Let's say you look at this first block here, and this is your redox reaction. Now you know that you assign oxidation states +3 for the iron, 0 for copper, +2 for copper, and then +2 for iron. So then my iron goes from +3 to +2. Is it oxidized? Is it reduced? It is oxidized because it is reduced, because it's going down in number, it's gaining an electron, so it's reduced. And copper is going from 0 to +2. It's becoming more positive, so it's oxidized. So when you look at a table, for example, I'm going to show you on the next slide like this, you would look at where are your half cells for the particular reaction that you have. So we have copper and an electron to make copper plus here, but that doesn't apply to us because we have copper 2+. And we have iron 2+ to iron 3+. So you would look at the table until you find exactly the half reaction that you want. And then once you have them, for example, here's our iron. And once you find your copper, then you would be ready to write down your half reactions as so. So then, here's I'm trying to find, the copper one might not be on here, but just know that these are two snippets of two, oh, there it is. Here's our other reaction. So then you would write it down. But note, are both of these, is the way that we write the reaction reduction or oxidation? They're both gaining. So they're both written in a reduction form. So what we have to do is we have to figure out, well, which one's being oxidized, which one's being reduced. Well, we already figured that out. Iron is being reduced, so you don't touch anything on that reaction. But copper is being oxidized. So what we actually have to do with copper is we have to flip this reaction. Whoops. Because this is being oxidized, this needs to flip. So I'm actually going to flip that and write it up here. I know it's written down here for you already, how to balance a cell reaction and calculate the standard cell potential, you reverse the reaction. So then that would give us this. Copper makes copper 2+ and 2 electrons. So you always want to sum up your reaction. Now, in order to get rid of electrons, right, we already learned about how to balance redox reactions. You don't have to add any hydrogens or waters here, but you do have to multiply the bottom by 2. Now, here, you do not touch the cell potential when you manipulate an equation with multiplying by 2 or 3 or etc. Now you can see that your 2 electrons will cancel, and you're left with copper plus 2 Fe3+ makes copper 2+ and then 2 irons. And then you would sum up your equations, where you have to make this negative because you flipped the reaction. So negative 0.34 plus 0.77 gives you negative 0.34 plus 0.77. That gives you point. So the E cell is therefore equal to 0.43 volts. So you do not manipulate the voltage when you multiply the equation to get rid of the electrons, but you do if you flip it for the oxidation form, you have to make the sign different. But then you just sum it up for the cell potential, like when we sum up a reaction to get back to our original equation. So these are our standard electrode potentials at 25 degrees. This is always your reference as you're doing your homework, the worksheets, quizzes, etc. Let's look at a self-check problem. So I want you to try and do this problem as an engagement. Consider a galvanic cell based on the following reaction. Aluminum ion and magnesium makes aluminum solid and magnesium ion. The 2 half reaction cells are also already provided for you, and you want to give the balanced cell reaction and calculate the electric potential, the cell potential for the overall cell. Now, note that if this wasn't given to you like this, where you weren't given the cell potential reactions, you always have them handy because you have that table that you can always reference to. So do this as an engagement, and then you will turn that in at the end of the day. Now, our goal is always spontaneous. Why? Well, spontaneous means that you do not need to continually put work in to make this reaction happen. So we are always looking for a spontaneous reaction, especially in the process of galvanic cells, because when you have a galvanic cell, your goal is to make a reaction spontaneous, because that's the definition. It's electric work from a spontaneous reaction. We'll talk about how to solve for non-spontaneous reaction after this, but we're still focusing on being spontaneous. If you are given two half-cell reactions like this, and you're not given an overall equation where you can assign oxidation states and say what is being oxidized and reduced, you have to determine through their voltages. So if you are given here, for example, the two half cells of nickel and manganese, you would determine their oxidation and reduction potentials based off of their cell potential voltages. The half reaction with the more negative electrode tends to lose electrons. It's oxidizing. And the half reaction having more positive electrode potential tends to gain electrons. It is reducing. So between these two numbers, which one is oxidizing and which one is reducing? Well, my manganese and the two electrons to make manganese solid has a negative 1.18. It's more negative, so this one's being oxidized and nickel is being reduced. Therefore, the oxidation reaction has to be flipped. So then I would get something like this. Nickel 2 plus 2 electrons, nickel solid. Nothing changed here. And then my other reaction flips. And now I have to make this positive. And I sum up my reactions. So you can see I don't need to manipulate my reactions because my two electrons cancel. And remember, your goal is to always get a positive cell potential. So now, if you take the 0.23 and 1.18, are you going to get a positive cell potential? Take a moment to think about that. Well, if I sum up negative 0.23 plus 1.18, I would get 0.95. And that's a positive number, so I'm spontaneous. Awesome. So even when you're not given the reaction, you can find it and then always double check. 2 plus to 0 for nickel is reduction. 0 to 2 plus for manganese is oxidation. And you have your overall cell potential using the voltages of the half cells. Now here we have another self-check. So describe completely the galvanic cell based on the following reactions under standard conditions. So this problem basically takes everything into account. So what I want you to do is write the cell reaction, calculate cell potential, draw a diagram of the cell, and notate the cell with the notation we learned. So remember, you look at which one's more negative, so I can help you a little bit to get you started. Which one's more negative here? 0.77, right? So this is oxidation. You would flip this. Therefore, this is reduction. So you have your silver, and then you flip your iron, Oopsies. Hold on. Let me go back. Plus electron. Then you manipulate. You know this is going to be 0.8. This would be negative 0.77 because we flipped it. Electron cancels. And what's your cell potential? Take a moment to calculate that. 0.03. Now, is this spontaneous or not spontaneous? Spontaneous. Very good. So we have the reaction. No, I'm being a little lazy right here. To write the complete cell reaction, we need to make sure it's always balanced, and we are writing our states of matter. So always write your states of matter. We know all ions are aqueous and metals are solid. And we calculated the cell potential. So now I'm going to leave the rest to you. Knowing what is reducing and what is oxidizing, draw a diagram of the galvanic cell with a porous disc, since you're not given information of a salt bridge, and notate that cell. And then you'll submit that at the end of the day. Now, talking about cell potential, free energy, and equilibrium constants. So we've discussed and learned that a positive cell potential is a spontaneous reaction. And in thermodynamics from Chem 1A, you should have talked about delta G, Gibbs free energy, and how that helps also to determine a spontaneous reaction. Now, we know that, therefore, cell potential and free energy should be related. However, we also learned that it can be related to equilibrium. So our Gibbs free energy, our cell potential, and our equilibrium are all related towards one another through different equations. So the work that is accomplished when electrons are transferred through a wire, we already discussed, depends on that push behind the electrons. And this driving force, the electromotive force, the electrode potential, is the potential difference between the 2 points in the circuit. So we're looking for that amount of work that's happening during this process of the transfer of electrons. We look at work as a point of view of the system. So work's always negative. And the max work gives the maximum cell potential. So we look at it like this. If I start to quantify, I look at the energy is equal to the work of a system over Q, where my cell potential is joules over my coulomb, my work over my charge. Well, I can rearrange this equation to get work is equal to my charge times my cell potential. And I can quantify this Q to something called a Faraday's constant, which then gives me that work is equal to, if I move the negative over, negative QE, and then I quantify my Q to be my number of moles times my Faraday's constant, which is 96485 coulombs per mole electrons. So your Q, your charge, is this constant times the number of moles that you have. And we can then place that back into the original equation. So when current flows, some energy is always inevitably wasted because you have frictional heating. So you can never really get the max amount of work. In any real situation, in any real spontaneous processes, the actual work is always less than the calculated maximum. So the actual work done is given by work is equal to negative QE. Well, how can that relate to our Gibbs free energy? The change in free energy actually equals the maximum amount of work that can be attained from a process. So work max, the maximum amount of work, is equal to delta G, Gibbs free energy. So for a galvanic cell then, since we know that the maximum work is equal to the charge and cell potential, max cell potential, that'll then be substituted by delta G. And since we know that Q is equal to NF, we can substitute everything to get delta G is equal to negative, to keep that negative sign, NFE max. And that's how our potential, cell potential, and our delta G, Gibbs free energy, are directly related. So the maximum cell potential is directly related to the free energy difference between the reactants and the products in the cell. The N is your moles, right? The mole difference between reactants and products. Galvanic cells run in the direction that provides a positive cell value. Because a positive cell potential is spontaneous and a galvanic cell is always a spontaneous process. A negative delta G is therefore also a spontaneous process. Just a couple more notes here so that you can then see that the E is the actual potential difference and Q is the quantity of charge in Faraday. So let's do a little self-check here. So calculate the Gibbs free energy, the standard. Again, note how here's a standard and not without the nod for the following reaction, and is this spontaneous? So first thing we want to do is figure out what is oxidizing, what is reducing. So I have +2, 0, +0, and then +2. So copper is doing what? Is it oxidizing or reducing? Reducing, because it's going from positive to 0. And this is therefore oxidizing. So then, if you want to calculate Gibbs free energy, what equation would I use? Delta G. This not just means that under standard conditions, negative NFE. Not. So if you're using the standard Gibbs free energy, you also use the standard cell potential. Faraday's constant is a constant. N is the number of moles of electrons. So then E you have to calculate. So therefore, I need to write my two half reactions. So I have my copper. And then I have my iron, but I'm going to flip my iron. My electrons cancel, and I get my reaction. Just double checking that I would get the same thing. And my E cell is therefore the sum, which is 0.78. So then I want to plug everything into my equation. Well, N is the number of moles of electrons. How many moles of electrons do I have? There's a change of 2. So I have negative, you keep the negative sign, 2 moles of electrons. My Faraday's constant, 96,485 coulombs per mole electron, times 0.78 volts, which is also joules per coulomb. And that gives you the Gibbs free energy is equal to negative 1.5 times 10 to the 5th joules. Because the Gibbs free energy is negative, this is a spontaneous process. Now, one more thing I wanted to talk about before we move on is how it's related to equilibrium. Well, the equilibrium reaction of Gibbs free energy related to K constant is delta G is equal to negative RT ln K. How can we relate this to cell potential? Well, we can derive the relationship between standard cell potential and the equilibrium constant for the redox reaction occurring in the cell by returning to the relationship from Gibbs free energy and equilibrium constant. If we then substitute delta G for that, what we know, how it relates to a cell, we would get the following. Well, I then, if I want just the cell potential by myself, divide NF on both sides. And I would get that the cell potential is equal to my R constant times temperature over moles, and Faraday's constant, ln K. The R that I use is in terms of energy, and it's at standard 298.15 Kelvin. Under standard conditions, then, the value of these numbers can be found. So what I can do is I'm going to erase this and go down here. So, to get more of a actual value for this, what scientists did is they plugged in standard values. So, for R, we used 8.314 joules per mole Kelvin times 298.15 Kelvin over 1 mole of electron and Faraday's constant, and then ln K. Which, to plug everything in, we would then do log. So then our equation turns out to be E cell is equal to 0.0592 volts over N, the number of moles, log of K. So that's just using standard values, where E is a cell potential, N is the number of moles of electrons transferred into the redox reaction, K is the equilibrium constant for the balanced redox reaction. Again, K is product over reactants. Now you can use this equation to find the cell potential, or you can use this equation to find the K equilibrium constant. And that's how they all relate together in a relationship. So take a moment for your engagement question to calculate the standard free energy change for the reaction at 25 degrees Celsius. Refer to the list of standard reduction potentials and submit this question at the end of the day.